Let's learn how to use the rules of block algebra so that we can later solve problems involving block diagrams. First, let's understand what the components or elements of a block diagram are. Here, we see this block diagram, which is quite simple, where we can identify different elements. First of all, we have the elements known as blocks themselves in this case, block G and block H. We will refer to this as an element of a block diagram in a controlled system. There may be different elements like these, each representing one of the systems in our process. Additionally, in a block diagram, we can also find signals. Signals are variables that can be represented by any letter. In this case, the signal X, the error signal E, or the signal Y, which is the output signal. These signals are actually the arrows that we see here in the block diagram. We can see that a signal only has a single direction. So, the signal X, which is an input signal, has a direction that enters this element. In this element, which is this circle, a signal E comes out, which is the error signal. And we also have here that from our element G, which is our block, there is a signal coming out, which in this case is called Y, and it would be this arrow. Remember, the signals are the arrows, and they only have a single direction. Additionally, in the block diagram, we can find another element, which is the summing point. This summing point indicates that it will take two signals and either add or subtract them. Depending on the signs at the summing point in this case, this summing point has two opposite signs, that is, a plus and a minus. This means that here, we are subtracting the signal X minus the signal coming out of this block, H, and that subtraction will result in this signal, which would be an error signal. I'm simply comparing the error between X and the signal that comes out here at H. But additionally, in a block diagram, we can also find these points, which we know as branching points. Basically, if we notice that our output signal coming from block G, called signal Y, we see that here we are obtaining that output signal. However, we can branch that signal, which means we want to send the signal Y to another point in the block diagram. In this case, we are branching it and sending the same signal Y to this block, H. So now we've learned how to identify the four main elements that make up a block diagram. When we are faced with a block diagram exercise, like the one we have here, for example, in this presentation, the most convenient approach is to start reducing each of these elements until we reach a simplified form, or a result that is a bit cleaner or more simplified, so we can truly understand how this control system works. What we're going to do, then, is simply take small sections of this block diagram, which is quite large, and start reducing them. Let's suppose that we initially take these two elements, and work with those two elements to either reduce them or swap them, change them. We'll see what we can do step by step. Different elements within the diagram to perform specific operations on each of these elements, using as a basis, for example, those two elements we selected, which were two summing elements that we have here. Let's see what operations we can perform with these two summing elements. All these operations we're about to see correspond to block algebra. And so, it will be important for us to learn how to differentiate and perform each of these algebraic operations. In this case, we'll start with some operations that are done with the signals again. The signals are the arouse as well as with the summing points and branch points. When we have two summing points, let's suppose that here we have a signal A and a signal B. We can perform operations with these two elements and transform them into another element that is completely identical or equivalent. But first, let's understand what we'll have here at the output Y. For that, let's take our first summing element, which in this case is a subtraction. Let's see what we get at the output of this element. Here, we can obtain a signal, which we'll call Z, and we'll see that Z is simply the subtraction of X minus A. That way, we have our signal Z, which is entering this other element. In this other element, it's a summing element. So, we see that at the output of the summing element, we have the signal Y, as we see here, which is simply the signal Z entering here, and the signal B entering from below. However, we know that Z is equal to X minus A. If we substitute that value for Z here, we have that our output signal Y is simply given by X minus A plus B. Now, if we want to perform operations with these two summing elements, something quite typical that we'll do in a block diagram is to swap these two components. In other words, this summing block, I can move it to the right, and this one here, I can move to the left. This will be especially useful later on, when we start solving exercises with block diagrams, and you'll see why. However, when we do this kind of operation swapping elements from one place to another or transforming one element into another must always make sure that our output remains unchanged, because no matter what changes we make here, I have to make sure that the changes I'm making are equivalent and don't alter my system in any way. So, if we make that swap, we can see down here that I've already switched the sum and placed it at the beginning. And this other sum, which is actually a subtraction, I put at the end. Let's see if it's still the same if I haven't changed anything by swapping them. So here, in this sum element, we can see that I have the signal. Z, in this case, will be the sum of X and B, Z. It's equal to X plus B here. Obviously, since I've swapped them, it's going to be different from this output signal. But what I need to check is that the output, as a whole, remains constant. Alright, Z. So, it goes into this subtraction element in this case, and here at the output. And so, I'm going to have Z minus the signal that's coming in here, Z minus A. However, we know that Z is equal to X plus B. If I substitute that in, here we'll see that Y equals X minus A plus B, which is completely equivalent to the original element I had. So, with this, it's proven that I can freely swap the addition elements from one place to another. Another operation we can perform with summing elements is the following. Here we have a summing element, but in this case, this summing element is adding three signals, a signal X, the signal A, and the signal B. With this, we now understand that a summing element is not limited to just adding two signals. It can add 3, 4, 5, even 1,000 signals. Just to be clear, it can handle 1,000 signals. Here, it would be difficult to represent, but in this case, since the summing block is taking three signals, we see that at the output, we will have the following. The summing block is adding X and B, which are the two elements with a plus sign. and it is subtracting the other signal, minus a, which is the element with a minus sign. When we have a block like this with several signals entering a summing element, we can split that element into multiple blocks. In this case, I can split it into 2 blocks. So I can initially separate here a block that will be x minus a, and this will come out here. In this signal, z is equal to x minus a, and z will enter this other summing element. So here at the output, y, I will have z plus b. But we know that z is equal to x minus a. If I substitute here, I will get that. Y is equal to x plus b minus a, which is completely equivalent to the output we had here. And again, I want to emphasize that here we've made a change to simply split this summing element into 2 summing elements, but we maintain the equivalence. We can see that here at the output, we have exactly the same signal. With this, we now understand a second method that we can apply to summing elements. However, we can also apply these concepts to branching elements. In this case, we have a signal x, which is this arrow, and it's exactly the same signal. In other words, the input signal x is equal to the output signal y. When we have branching elements, as we've already explained, we're simply taking the signal, whether it is, I can call it x, or I can call it y, and I'm sending it somewhere else. For example, here I'm sending it upward in the block diagram, and here I'm sending it downward. When we have branching elements, I can also swap these branching points. In other words, the one that was going downward, I can easily place it here at the beginning, and the one that goes upward, I can put it here on the right side. And we can see that, in reality, nothing is actually changing, because this point is exactly the same, it's just here. It's the same signal that's going in several directions. This swapping of branching points will also be very useful when we start working on exercises with block diagrams. However, it's also very likely that when we're working on block diagram exercises, we'll come across the following situation: a branching point next to a summing point, and many times we might want, for example, to move our branching point to the right side of the summing point, or vice versa. Maybe we want to move our summing point to the left side of the branching point, which would actually be the same thing. However, this isn't possible to do. So when we encounter this situation, we need to look for other points within the block diagram to try to solve it, because when we have this, it's not possible to do it. At least, there isn't a simple way to approach this kind of situation. Let's take a pause here if you go right now. In the description of this video, you'll find a link that will take you directly to the website Control Automatico Education.com, specifically to the section on block diagrams in our Feedback Control Systems course, right here. There, you'll find exactly everything we're covering. For example, here we see what we just discussed about a block diagram. What are the elements that make up the block diagram here? And you'll also find all the mathematical operations that we can perform with block algebra. Here, you'll see everything you can do with signal, for example, summing signals, the sum elements, and what can be done with block elements, all the available mathematical operations. As we'll see in this video, if you master these operations, you'll be able to solve any block diagram exercise. However, what I wanted to show you here is that you can download this table by clicking on download. When you click on the table, it will open this table, which I extracted from Ogata's book right here. So here you have all the operations that we can perform in block algebra, and these operations. This table will be essential for you to have on hand, and we'll be using it in the upcoming videos as we solve exercises involving block diagrams. However, we haven't yet covered the operations with blocks, so let's quickly and intuitively understand how these block operations are performed. By the way, I'd love to know in the comments, what are you currently studying in your control systems course? And let me know if what we're covering here is helpful to you. I read all your comments. Alright, so let's understand how to approach algebra when we have blocks. Let's start with the simplest case, which is having 2 blocks in series. In this case, I have block G and block H. Let's see, then, what we have at the output. If we look here, initially the signal X, which is this arrow, is entering block G. That means that at the output of this block G, I will have a signal occurrence which would simply be the product of the input signal X and the block, so X times G. This signal Z is then entering block H, which means that at the output of represented by this arrow, which we'll simply call ULC, that Y equals Z times H. However, Z is X times G, so I can substitute Z here, and you'll see that my output Y is simply X times G times H. In the same way we did with the summing elements, I can think about swapping these blocks. So I can place block H at the beginning and block G at the end, and we'll see that this equality is maintained. Here, once again, at the output of block H, I have the signal Z, which in this case is the input signal X times H. This signal Z will then be multiplied by G, so Y would simply be the signal coming in, which is Z times G. But we already know that Z is X times H, so Y is X times G times H, which is exactly the same as what we had in our original block. So always keep this in mind. Whenever you perform a transformation of the block diagram into another equivalent transformation, you must make sure that the output you get is exactly the same, so that you can confidently state that it is equivalent. However, when we have these 2 blocks in series, the most interesting thing to do is to combine the 2 blocks into a single block, which results in a much more simplified form, as we see here. We have reduced or eliminated a block. Now we simply have a single block that represents the product of the 2 blocks, G times H. We'll see that this maintains equivalence at the output. If we look, X multiplies all of this, so X multiplies G times H. Another of the most popular structures we'll encounter is this one, the parallel structure. It's one of the most important, because we see that the input, which is X, enters both G and H in parallel, and both are either added or subtracted. And of course, we know that the summing element can be either addition or subtraction, it doesn't matter. At the output, we have the signal Y, and let's see what we get in this signal. Initially, if X multiplies this block G, then at the output of G, it'll have X times G. Similarly, below, if X multiplies H, at the output it'll have X times H. We reach the summing element, So at the output of this summing element, I have my y, where y will be equal to the sum of these two, that is, the sum of x times g, or in this case, the subtraction minus x times h. Perfect. Now, how can I transform this block diagram into an equivalent one? Let's transform these parallel blocks into a single subtraction block. This single block will have g minus h, and we'll see that it's completely equivalent to what we have here. If x multiplies this block g minus h, then in my output y, it will simply be x times the block, and the block is g minus h. If I apply the distributive property here, you'll see that I arrive at exactly the same signal we had initially. So this demonstrates how to handle blocks in parallel. A second operation we have, and that we'll use a lot, is to switch the branching points from one side to another. In this case, we have a single block g and a branching point. What we want to do here is move the branching point to the other side. But first, let's see what we have at the output. Always do this so you understand how to work with block diagrams. Here at y1, then, we'll have x times g. Why? The signal x multiplies block g. So here at y1 I have x times g. What do I have at the output y2? I simply have x. So y2 is directly the input x. When I move the branching point from the left to the right of my block g, I need to maintain equality at both outputs, y1 and y2. Let's do this. Initially, the first thing we do is move the branching point to the right, and that's what we did here. Now, let's check after doing this if it really is equivalent or if it matches the original. Let's look at what we have at y1. y1 equals x times g. We see that x multiplies g and comes out here at y1, which is what we have here. Now, let's see what we have at y2. y2 is also x times g. How is that possible? Here, x is multiplied by g, so of course, we end up with x times g coming out at y2. But this doesn't match what we originally had. Here, we should only have x coming out, but instead, we have x times g. In other words, we need to remove this g. So how are we going to eliminate this g? So simply, here in the feedback loop, we need to multiply by the inverse of g. If we do that, if we multiply here by the inverse of g, you'll see that now, the g that was here will cancel out with this g. And at my output y2, it will be equal to x, which is exactly what we had originally. So whenever we want to move a branch from the left to the right of a block, we simply move it, and in the feedback branch, we multiply it by the inverse of the corresponding block that we have skipped over. The opposite case can also happen, where the branch is on the right, and I want to move it to the left. So let's first look at what we have at these two outputs. Here, there are two outputs. At output y1, I have x multiplied by g, as we see here, and at output y2, it's the same. I have x multiplied by g coming out at y2. Now, let's move the branch to the left. First, we move the branch and check if we have maintained equivalence. Again, here at y1, x times g. So that gives me y1 perfect. It turned out exactly the same. Now let's look at y2. At this moment, what is y2? y2 is x, so it didn't match this here. I'm missing ag, so it's not equivalent. But you can already see that I need to add ag here. To add it, I simply need to place a block here at the branching point. That way, at y2, it will indeed be x times g, which is exactly the same or equivalent to what we had in the original diagram. So now you can see what the strategy is. Always try to achieve the same output signal. If you do it this way, instead of memorizing that when you move the branch from right to left you have to add a block at the branching point, you have the freedom to study in the way that works best for you. But the easiest way to understand it is always by performing these output operations, and always checking that equivalence is maintained. Up to this point, I think it's important for you to understand that if you want to keep learning about control theory and want to keep advancing in these topics, or if you want to learn about programming or microcontrollers, then what's coming up on this card? Did you know there's a card? If you check out what's on that card, it will help you boost your skills tremendously in these areas. Now, let's also take a look. Since we've already worked with branching points, let's work with summing points. Summing points can also be moved from one side to another within our block diagrams. In this case, we have the output y1. Let's see what we have here. We see that x1 is subtracted from x2. So here at the output, I have x1 minus x2, which is then multiplied by g. So the output y1 would be g times the difference between x1 and x2. What we're going to do now is move the summing point to the right of the block. Let's do that here first. So we move the summing point, which in this case is a subtraction, but it doesn't matter, and let's check if the equivalent is maintained. Here in y1, let's see, x1 times g gives me g times x1, perfect, and it's being subtracted here with x2 minus x2. So in y1, I have this equation. However, it's not equivalent to the original equation, because here I have g times x1 and g times x2, meaning I'm missing ag for this x2. Let's fix that. So let's add g to x2. So we see that when we move the summing block to the right of g, for the other signal that we're adding or subtracting in this case, subtracting need to add the block we've moved past, so we add the g block. Now, if we look here, y1 is equal to g times the difference between x1 and x2, so now it does maintain equivalence with the original diagram. Something important you need to notice here, so you don't get confused, is that it doesn't matter if you see the equivalence in this form or in this other form, both ways are the same. So what's happening here? The signal x2 comes from left to right and enters the summing point, but it can just as easily come from left to right and enter the sum, or it could come from top to bottom and enter the sum, or from bottom to top and enter the sum. It doesn't matter where it comes from. It's always equivalent. So don't get confused by. About the directions, let's notice that the arrows or the signals always indicate where they are entering. Now, what happens in the opposite case, when we have the block or the summing element to the right of my block? Initially, let's see that at the output we have x1 times g. So x1 times g, which in this case is subtracted by the signal x2. When we have this, and we want to transform it, we're going to move the summing element to the left of our diagram, our block. Let's do that first. We move the summing element to the left, and we're going to check if this condition is maintained. Here, initially, we have that, and y1 we're going to have x1 minus x2, which is what we have here, and that subtraction is being multiplied by g. If we distribute, we'll see that it's g times x1 and g times x2, and we see that it's not the same as what we had initially. Here, we have an extra. What's left over is that g. So we need to remove that g. How are we going to remove it? That g that is entering here in the feedback, in this x2 branch. So, in this x2 branch, we're simply going to insert the inverse of g to cancel out the g. So right here in this branch, we multiply by the inverse of g, and now we can verify that at the output y1, we get g times x1 minus x2, which is exactly the same as in the original diagram. And again, just so you don't get confused, this is the same as having it like this. Here it goes from left to right, but it can also go from right to left, from top to bottom, or from bottom to top. So again, don't get confused by this. And finally, we're going to arrive at one of the most important diagrams or simplifications in the field of control. This diagram, just like the parallel one, is one of the most important. This is the famous closed loop feedback. Let's understand, then, how to simplify a closed loop feedback. Here, we have feedback because we see that there's a loop. The arrows, if we follow them, form a direct loop from left to right, meaning that the signal x, which is the input signal, travels through various blocks, summing elements, and branches, and reaches the direct output perfectly. However, there is a signal that is being fed back to the input, and in this case, it passes through this element h. That signal being fed back is a feedback signal. I'm feeding the output back into the input. So how do we solve this diagram? Easily. Initially, the signal coming out of this block diagram is labeled I. You can name it however you like, but it's usually called E, which stands for error. The signal E is simply the difference between x, which is the input arriving at the plus point, minus what is entering here. So what signal is entering here? It's simply the signal coming out of h. And what signal comes out of h? It's simply h times y. We see that y is multiplied by h, so that's the signal entering here. Therefore, the error is simply x minus h times y. Now, looking at g, the signal E is entering it. So at the output of this block g, we have our signal y, which is simply y equals g times the error signal. With this, and substituting the error here, we have y equals g times x minus h times y. If we apply the distributive property, we'll get y equals gx minus gh times y. Here we have a y, and here we have another y. Let's take this term that's being subtracted and move it to the other side of the equation with the opposite sign, meaning well added. So it becomes y plus g times h times y equals gx. Now we factor out y, so we get 1 plus gh times y equals gx. We simply move 1 plus gh to the other side of the equation by dividing. Having done that, we now know the value of the output y in relation to the input x. So this entire block diagram can simply be reduced to a single block, which is g over 1 plus g times h, which is what we had here. Notice that, for example, if you do the exercise and instead of putting a minus sign here, you put a plus, you'll see that this sign here, which is currently a plus, will appear as a minus. So with negative feedback here, a minus sign will show up as a plus. This is the representation of a closed loop diagram, and it's one of the most important in the field of control. As always, when solving exercises with block diagrams, we should always try to break down our block diagram or exercise into smaller structures, whether in parallel or in feedback, to simplify our diagram. So, when we have those large blocks we saw at the beginning of this presentation, we should always try to reduce them either into elements that are always in parallel so that in the end, everything is in parallel or into elements in feedback. This way, we can reduce any block diagram as much as possible. Again, remember that you can download the table from the description. This table summarizes everything we've just covered and is what we'll start using in the next videos to solve exercises. Now you know how to obtain each of these elements. If you master all these operations we've just discussed for block diagrams, you'll be able to solve any exercise you encounter. To keep learning, I invite you to subscribe to this channel by clicking on my photo, and also to check out our control systems playlist. I also invite you to watch the next video on block diagrams, where we'll work through our first example.